Insect exhibits impressive locomotion behaviors and excels at adapting to terrain and amputation perturbations. This is largely due to their deep distributed neuron clusters, and inspired by this, we implement our DNLC on a modular platform, ICRA, which in each of its modules, there is a microcontroller unit for compute, and here we mimic both insect morphology and also its control architecture. Previous works has achieved CBG locomotion, but its control architecture and hardware are usually not distributed to the joint level, and usually they cannot adapt to both terrain and amputation perturbations, which is significant because this requires both intralimb and interlimb adaptation. And that is the two parts of our methods, interlimb and intralimb coordination. For our intralimb coordination, we place a CBG oscillator on each joints of one leg, and its output is modulated by joint position, joint load, and joint velocity, or the local proprioceptive feedbacks. And we further influence the outputs with interlimb influences, which are categorized by 3 rules. Rule 1 inhibits the start of swing phase. Rule 2 excites stance to swing transition, and Rule 3 does the same thing, but in a more gradual manner. And with this control architecture, we're able to achieve 6-legged locomotion on flat ground, and here it self-emerges to a 9 tripod gait. For our experiments, we set up our experiments with a motion capture system that tracks the robot torso's odometry data. We also track the swing and stance phase data from each leg of the robot. So for some qualitative results, we have a grassy hill terrain that's uneven, and with predefined tripod gait, it is not able to climb up, but with our DNLC, it is able to traverse through the terrain with relative ease. So here it is climbing up the terrain. And for our amputation trials, we have symmetrical and asymmetrical amputation. With symmetrical amputation, we have a configuration that's similar to a quadruped. With predefined tripod gait, it is not able to move forward, but with DNLC, it is able to move forward with alternating leg motion and also adaptive stance duration. And with our asymmetric amputation, with predefined tripod gait, it's going to turn at every time step. But with DNLC, it is able to walk mostly straight after some initial adjustment. So we lock down our performance as forward curved linear motion. We compare the velocity decrease of all of our perturbation trials against the 6-legged flat walking counterpart. And we are able to achieve 31.3 average increase with DNLC, showing that DNLC is much less perturbed by hill and amputation perturbations. And we attribute these performance increase to 2 emergent behaviors. One is phase difference, and another one is stance duration. Here we lock down the phase difference as swing probability on 6 legs, and this indicates out-of-phase relationships with immediate neighboring legs alternating motion. And here we lock down all of our trials phase difference. A phase difference of 0 means the leg pairs are perfectly in sync, and a phase difference of pi means they are alternating behavior. And in our case, with DNLC, almost all of the legs of immediate neighboring pairs are able to achieve more out-of-phase behavior. And the second emergent behavior is stance duration, and we noticed with increased load, the stance duration of each leg becomes longer, and this is also observed in biology. So for our future works, we plan to implement modular RL policies for distributing control, and in fact, we have put our interlimb coordination with bio-inspired rewards with RL, and it works really well with locomotion, and we are going to further improve that with distributed control. We also want to implement tactile tarsus sensor, curve walking, and better design of feedback functions with insect data. So please check out our website for more information. And I would like to thank all CMU Biorobotics lab members and ICRA engineering team for building and testing the modular platform. Thank you.